Physics Bites.
Physics Bites,
A science podcast in English by the students of Notre Dame d'Ascension.
Hello and welcome to Physics Bites, the English language physics podcast of the students of Notre Dame d'Ascension here in Paris. We have our new episode for this week out with our junior level students. I have 4 new experts who are here to talk to you about nuclear energy. So I'm going to let themselves introduce themselves and then we'll get right to it.
Hi, I'm Celeste.
We have Celeste.
Hi, I'm Colombe.
Colombe.
Hi, I'm Clement.
Clement.
Hi, I'm Emma.
And Emma. So you guys, in the framework of our junior year project about the new forms of energy and climate change, you guys were focused on nuclear energy. Now, nuclear energy, we know a fair bit about because we already had one of my students in my senior level classes who did something on it, but you guys did a pretty complete presentation on the different aspects of it, mostly fission, some also on fusion, different types of nuclear reactors, and we're going to go over all of that in detail, and then we'll see if there's anything that you weren't able to talk about during the presentation, and then we'll bring it in. Okay? So I'll leave the floor to you guys. You guys can maybe just give us an overview of what we mean by nuclear energy, and then we'll start going into every single details. Who wants to get started here?
I can.
All right, so Celeste is going to start us off.
So first of all, we interviewed a specialist in that field.
Mm-hmm.
And so globally, around 10% of our energy comes from, of our electricity comes from nuclear power.
So we're talking at a planetary scale, all countries included.
Yeah.
That's not really the case in France because we have much more nuclear power. So
75% of France's electricity is nuclear.
Right. So France is the only country in the world that has that much electricity coming from nuclear. And it was a political choice, I guess, that was made a few decades ago, which is paying off now in terms of carbon emissions and energy independence. But I'll let you continue.
So nuclear energy is one of the most resilient, environmentally sustainable, and reliable energy sources. It doesn't depend on weather or time of the day, and
which makes it an ideal source of energy for what we call base energy, right? Something that is constant, that doesn't depend on external factors, right? So for base load, it is kind of ideal, similar to coal and to gas and to oil without all the carbon emissions.
Yes, exactly.
Okay. So what do we mean exactly when we talk about nuclear energy? What does that engender? Is it just like one form of energy? Or is it different types of things? What do we mean by nuclear energy?
So we have 2 processes.
Okay.
So one is fission, and I'm going to talk about it, and the other one is fusion, and Clement is going to talk about it.
Okay. So fission and fusion, which is the one that we use currently?
Currently it's fission,
right,
because fusion isn't as developed as fission, right, and it's actually hard to reproduce the conditions we need to get fusion on Earth.
Okay, and I'm sure Clement is going to go into details about that. Yeah. So let's get started with the one that we do know about, fission energy. Do you want to maybe give us a very brief history of fission as a source of electricity? Any of you guys talked about it in the 20th century? This is a very recent sort of development, right?
Yes.
So Celeste, just a very brief background.
There was Marie Curie and Pierre Curie who laid the groundworks to this energy.
At the very beginning of the 20th century.
And we also have in 1938 German scientists Otto Hahn and Fritz Strassmann that discovered nuclear fission.
Mm-hmm.
Yeah.
So radioactivity was mostly in France with the Curies and Becquerel, and nuclear fission, the way we think of it today, is mostly a discovery that came a few decades later when we had more knowledge of the atomic structure of matter. And then right after that is when we had the Manhattan Project.
Yeah, exactly. During World War II, it started in the 1940s. And then we had a peaceful project because they created bombs and everything.
Right. So the Manhattan Project was the project to produce a nuclear weapon from it.
Yeah.
But what you're saying is that right after the war was over, much of that knowledge was used to get into what we call civil nuclear energy. Okay. Okay, go on. So let's come back to Emma, who was talking about nuclear fission. So how do we produce energy from nuclear fission?
So we should maybe
talk about what fission is.
So we all know that atoms are made up of 3 particles. So we have the nucleus, which contains the protons and neutrons, and we have the electrons, which are all around. And so the nucleus contains a lot of energy in the bond that keeps the nucleus together.
Right. Just to make a comparison, you use the word bond. Is this the same as like a chemical bond, or is it different? I know the question is beyond your junior level physics. No? So it's much stronger than chemical bonds, because chemical bonds involve which part of the atom? We did this last year in grade 10.
Electrons.
Right. The electrons which are outside of the nucleus, whereas the energies necessary to keep the nucleus together are many orders of magnitude more intense. So when we're talking about a nuclear transformation, we're talking about huge amounts of energy. Okay.
And so this energy, we can use it when we break the nucleus apart. We can use it to make nuclear energy. And so
how do we break the nucleus apart?
I was going to say
there we go. I
so
anticipate your
fission
question.
occurs when you have a very heavy, unstable atom, and it's going to be, a neutron is going to collide with the...
So let's make the distinction between 2 types of disintegration, right? There is disintegration which happens sort of naturally, spontaneously, and then there is disintegration of the nucleus that happens when we sort of force it to happen, right? One of them is called just sort of natural radioactivity, so what happens in nature. What you're talking about is stimulated fission, right? So we incite it to happen by sending this little powerful, this energetic neutron, and sort of the nucleus is already very unstable and it wants to go apart, and we're like okay, here, go, break apart. Okay. And then what happens when the nucleus breaks apart?
And then when it breaks apart, you get 2 byproducts, which are smaller and less heavy atoms. And it also releases neutrons, which when it hits other heavy and unstable atoms, are going to keep the chain reaction going.
Right.
And so when it breaks apart, the nucleus breaks apart, you have a lot of energy which is released. And so
what does this energy look like? What form does it take, this energy that's released generally?
It's mainly heat and radiation.
Okay.
And so that heat is going to be harnessed and used to produce electricity in nuclear reactors.
How do we harness that energy?
You have the nuclear reactor. The chain reaction is going to occur inside the vessel, and you have what is called a coolant, which is going to circulate through the reactor, and it's going to go through other circuits. And when the fission occurs, we have a lot of heat that is going to come off the fission, and so the coolant is going to take all of that heat and become steam.
Right.
And so the steam is going to turn turbines.
Right.
And the turbines are going to generate electricity.
Through a generator. So the idea is not too dissimilar to the way we produce electricity from, for example, coal or any kind of combustion, because in both cases we're producing heat, and the heat is creating steam, and the steam is what's turning the turbines which produce the electricity. The main difference here being that we produce that heat not through burning, but we produce it through fission, which is much more efficient, has much more energy, and it doesn't emit any kind of greenhouse gases, which is what the main advantage of nuclear energy is. Okay, so that's the basic idea of how nuclear fission works. What do we use for nuclear fission generally?
So we have 2 types of reactors, mainly 2 types. Right. So the first one is pressurized water reactors, which we call PWR. And so we have 2 circuits. we have the fuel, uranium fuel, which is inside the vessel, and so the chain reaction of fission occurs, and the water, which is going to circulates through that reactor to cool down the reactor, because it's going to heat up a lot. It's going to turn into steam and turn the turbines to generate electricity through the generator.
Okay, so this is the pressurized water reactor, which most of the reactors in the world are pressurized water at this point?
I think we're approximately around 60% of our reactors that are PWR. And we have another one which is also used a lot. It's the boiling reactor.
Boiling water reactor, BWRs, right?
Yeah. So the idea is the same, but we only have one circuit, and the water is going to boil inside the vessel. Okay. And then turn.
Is there an advantage to one compared to the other?
I read some things that said the boiling water reactor were less, like it was easier to maintain.
Right.
And it has I don't know if it has a larger input or not.
I think the problem with boiling water reactors is that generally they're more exposed to radioactive material, because the water is directly boiling where the nuclear fission fuel is, whereas the pressurized water ones, because there's this secondary circuit, so it has a longer lifetime, because the separating the water, which is the coolant, from the actual nuclear materials. Okay. You also talked about another form of nuclear fission, power plant, which is much less in use, but which potentially could be of much greater utility, which was the fast neutron ones.
That's the HTGR.
Okay. Do you want to maybe give us a very short summary of what that entails, what the difference is, why it's better or worse? If you guys remember.
I think it just.
So
I just remember that the HTGR's reactors that stands for high temperature cool gas reactors.
Okay.
And so they are really developing right like actually because I think they are known for using for emitting really less materials like CO2 and everything than the other reactors. But I just read some articles about them. But
okay. So I think that's different from the fast neutron reactors that I was talking about, right? So, but anyways, let's move on. I think Colombe wants to add something.
I know that they worked at like higher temperatures than the normal ones, we can say. So it is more efficient.
Right. So it's a question of efficiency in terms of, otherwise there's not a big difference in terms of how the basic idea of the concept is. Okay. Maybe we can move on to quickly talk about nuclear fusion, and then we'll come back because you guys gave a lot of information about, so different types of ideas that we have. But before we go there, one thing, what do we use as nuclear fuel for our reactors?
Uranium.
Right. So we use uranium-235. What does that mean, uranium-235? What does that 235 indicate? And we did this last year also.
Like it's an isotope of uranium-238.
Right, or of uranium.
Of uranium.
And 238 is another isotope of it. What is so particular about uranium-235?
When we use uranium as a fuel, when we use ordinary water, because it absorbs too much neutrons, we can't just use the natural uranium that we find in the nature.
Okay.
So we have to enrich it.
Right, which means what exactly? What is enrichment? What is uranium enrichment? What is it? What are we doing when we do that?
Because the natural uranium we find,
which is mostly 238.
238.
Okay.
It doesn't have a high concentration of U-235, which the concentration is about 0.7%. We need to get this concentration higher to approximately 3 to 5%, so that we can use it with ordinary water. So what we're going to do is enrich it.
Right. We won't go into details of enrichment process. It uses like centrifuges and like, having separation between different isotopes and like more concentrating on the one. Okay. So before we go to nuclear fusion, maybe we can talk briefly about so it's a very controversial source of energy, right? Nuclear energy. It's very powerful. France is the only country which uses it this much, and most other countries, our neighbors, Germans, they've stopped all of it. There's a lot of paranoia around it. There's a lot of fear. Why is that? What are some of the dangers associated maybe to nuclear fission as a source of energy? And how much of those fears are real fears and how much are not?
So there are several fears about that. First of all, the control of the nuclear wasting, recycling, and management. But also there were some safety and security problems, like the Chernobyl disaster in 1986. And also the Fukushima disaster in 2011. Mm-hmm. And this led to political challenges that, because nuclear is the most criticized, remains the most criticized source of energy in the world. And yes.
And so you talked about, for example, these two accidents. You talked about waste management. What is the problem of waste management? Why is that a big issue that we have to take care of? What is the when we talk about nuclear waste, you say that to anybody in the street, they get goosebumps and they're all afraid. What are the dangers of nuclear waste? And is it really that dangerous? Is it that much of a problem?
I know that there are two types of nuclear waste. Okay. The short-lived ones and the long-lived ones. And I think it's the long-lived ones that we have to care about more, because they stay on Earth for longer, yeah.
Right.
But I don't really know how this waste is really dangerous for our health or for the planet. But I know that they are maybe.
Well, the danger, I guess, would be that if it goes into nature, because the way we do it right now is it's in containers and we know where it is, and it's very...
it is very radioactive, and if it touches the water, it can contaminate everything.
Right, because water is what animals would feed on, what agriculture would use, and it sort of gets integrated, and that's the danger. Just very briefly, what are the physical dangers of radioactivity? Why is radioactivity so scary?
Celeste? It increases the percentage to
the chance
to have cancer.
Right.
And there were some studies about it. There were some epidemiologic studies of spatial variation in cancer incidence or mortality that have been conducted, and so the results were that children that were under the age of 5 years old have an increased incidence of having cancer
if they're exposed to radioactivity. Okay.
By 61%.
Okay, which is definitely non-negligible. I guess the issue is that we don't have a lot of data to study, because the two main incidents have been the two explosions during Second World War, which were very, very, very high doses of radioactivity, and then Chernobyl, which is a very locally contained sort of area, but then there was lots of nuclear radioactive stuff that went into the air and was sort of spread around Europe. Celeste?
One thing that people don't really know about it is that it can be also good for the health. If you're not too near the plant, it can be very good for your health.
And I think some studies exist, and so some researchers studied the place where the Chernobyl explosion happened, and the ecosystems are much more rich now. But it's years after the explosion, But
so I think you're referring to the fact that because of the 30-year anniversary, I think the World Health Organization did a study of the biodiversity where Chernobyl took place, the accident took place, and they found that indeed there's much higher radioactivity there than in where we usually live, but there's, at least statistically, they did not find cases of like unusual cases of like lots of genetic mutation or whatever. And the idea being that not that radioactivity is good for health, but that human presence was much more bad for health. And what happened is that because of radioactivity, there were no humans there. And so life comes back and biodiversity has gone up. And that radioactivity in and of itself was not causing any more or less rates of cancer because of the amount of radiation. Yeah.
I think it's also important to mention that, of course, nuclear waste management is really important, but there are a lot of projects that are being launched.
Yeah.
So maybe I can talk about it now.
Oh, sure, why not? Let's do it.
And there is really there is a variety of different projects. Like for example, there are long storage projects. So I know that one of them is the GGRs, which stands for Deep Geological Repositories. So nuclear waste is encapsulated and buried like deep underground in stable geological formations. So they are isolated for thousands of years.
Right.
And there are also a thing called immobilization. I think it's into ceramic materials.
Okay.
Because it's much more
it blocks the radioactivity. Yeah.
And so it's the same. It's buried and I
think it's interesting to note also that different countries have different approaches to how they want to manage the nuclear waste. Yeah. The Americans, for example, I think some Scandinavian countries, they're more about like, we should find a place deep inside the earth, we store it there. In France, we have a different approach to it.
Yeah, I know that in France, we have a project called MOX, but I think it's not only in France, it's also in other countries.
Sure, there are other countries. I think but in France, it's one of the main ways. We don't only store it. And what is MOX?
The idea is to recycle nuclear waste and to reuse it. In MOX, it's like an assembly of different nuclear waste that are reused to provide electricity. And I think it's like 60% of electricity in France that is produced thanks to nuclear waste that is recycled.
So the idea being that when we use our nuclear fuels, it's enriched, like you said, Emma, up to 3.5 to 5.5%. When we use it to produce electricity, part of that uranium-235 is used up. And when it goes below a certain level, it's not really usable. So the idea would be to re-enrich these wasted, nuclear fuel bars to get it back up to 3.5-5%, right? So instead of just saying, okay, we use it up, we're going to put it away, the idea would be to recycle it. The problem, with that is that it's a bit of a technical challenge. It might be costly, but at least we produce much less waste.
And to give an idea, since the use of this project in France, 18,000 tons of natural uranium has been saved for electricity.
Which is good because we don't have any uranium in France, right? We have to import it from other countries. There's a lot of uranium if I'm not mistaken, in Canada, in Australia, and also some African countries.
Russia and Kazakhstan.
In Russia and Kazakhstan, exactly. I forgot Kazakhstan is one of the biggest exporters of it. And it's better for our energy sovereignty if we can not be dependent on other countries, especially if there are countries where we don't necessarily agree politically or there's a conflict, right? Because our energy depends on that. So this idea of nuclear waste being dangerous, it is true, but what you're saying is that we know how to do it. We have been doing it really well, and we don't even have to store all of that nuclear waste, right? Do you guys know how much nuclear waste we have produced since we've used nuclear energy in the 1950s?
No.
No.
Celeste doesn't know. So if we don't take into account the volume of, because most of the volume of nuclear waste comes from the vessel that we put it into, right? The actual nuclear waste, if we think of all that we have used in all the countries, it would fill up half of our gymnasium. Right? So there's not that much, right? Compared to, for example, many other sources of energy that we use. Okay. Shall we move on to nuclear fusion, maybe?
Yeah.
All right, Clement. So let's talk about nuclear fusion. What is fusion compared to fission, and then how are we hoping to get electricity out of it?
Compared to fission, fusion is like the opposite reaction. It's two light atoms that combine to form a heavier one. It takes place in a state of matter that is called plasma.
All right.
Basically, it's a hot charged gas made of free-moving electrons, and it has unique properties distinct from liquid, gases, or solid.
Yeah. So, what conditions do we have to reach the plasma state specifically?
High temperatures.
Right. And when we say high temperatures, we're talking about like.
It depends of the environment. For example, in the sun, it's large, but in the sun it's like 10 millions. And
right. So we're talking like really, really high temperatures, right? Where do we find temperatures like this in nature?
In the stars of our universe.
Right, in the stars, in the sun, and in other stars, where the main way of producing energy for billions of years is nuclear fusion, right? Mm-hmm. So if we manage to find out how to do this, we have the potential to produce a lot of energy, right?
Of course.
Okay. So that's the idea of fusion. What do we use usually for fusion? What are the
to like produce?
Right. What are the elements? What are the atoms that are used most commonly to produce fusion? Right.
Isotopes of hydrogen. Because the reaction.
So the reaction uses hydrogen as a reactant, and then what does it produce?
No, it's used
deuterium, and tritium, yeah,
to produce helium plus one neutron.
Right. So the idea is we take two hydrogen atoms, basically, or two hydrogen isotopes, and we sort of, in these very extreme conditions, put them together, and they become a helium atom. Yeah. And in the process, that releases
heat.
A lot of energy, and heat.
Kinetic energy.
Okay.
Heat, and we are using this heat to convert it into electricity.
Okay. All right. So fusion has the potential to be more energetic, and the byproduct of it is helium, which is a gas that has no negative properties for us. It's not radioactive. It's not dangerous. In parties, we take it in to have a high-pitched sound. So, in and of itself, we like helium.
Yeah.
Okay. So, why don't we have fusion energy?
Because the conditions to make fission are really difficult, because it requires high temperatures and also high pressure, because the high temperatures provides an environment for plasma, and we need plasma to make fission. Right.
So in the sun, do you guys remember what the temperature in the center of the sun is, where most of the fusion takes place? Around
10 million?
Yeah, maybe 1 to 10 million Kelvin. But the pressure is really, really high.
Yeah.
On Earth, we cannot produce those high pressures. So we have to produce really high temperatures, right?
Yeah.
Around what temperature?
150 degrees.
Right, 150 degrees Celsius or 150 Kelvin. How do we do that? With great difficulty, but...
Yeah, but we manage to do it. But there's two types of way to produce fission. The one that is the most important is magnetic confinement.
Confinement, yeah.
And there's also the inertial confinement,
which uses
beam.
Lasers.
Lasers.
We use lasers.
Yeah.
So in the one case where the magnetic confinement, what is magnetic confinement? What are we doing with magnets here?
Here's the magnetic confinement helps to keep the heat inside and
maintain the plasma in a container without touching materials, because 150 million degrees, nothing can remain as solid, right? So it has to be inside a magnetic. Okay, and there's a specific sort of shape that we used. Do you remember what it's called?
Tokamak.
Right, we use tokamaks, which is
it's a type of which is
what does it look like? What is the shape of a tokamak?
Donuts?
Right, it's like a donut. It's like a little ring with a hole in the middle there. And how do we produce this very powerful magnetic field?
And that is the point of fission, because we have to produce the magnetic field. I think we need really high. We need a lot of electricity to produce.
A lot of electricity, because we have to use superconducting magnets, right? Which consume a lot of electricity to produce really, really powerful magnetic fields. Have we produced electricity from fusion?
Yet, it's very. I don't know how to say. No, not really, because because there is in China there's a lot of experiments, and
not just in China.
Yeah, in France too, because
there's a very famous big collaboration in the south of France, which is all the countries of OECD generally, I think, are participating in it. And so when you say not really, it kind of means we have produced electricity, but
we cannot maintain the reaction of fission in the tokamak, because it's really difficult.
The magnetic field, when it's containing that much energy, it doesn't remain stable for very long. But recently,
in France, we have stabilized the reaction for 20 minutes. I think
exactly.
At high temperatures. That's a great
accomplishment. So this is in the famous ITER site in the south of France, where we're building the world's first prototype of a fusion power plant with a big giant tokamak. And so I think it was a couple of months ago. They managed to hold a magnetic field and produce electricity for about 20 minutes, which was much longer than before. I think the previous record was 15 minutes or something like that.
Actually, it was 15. Yeah, about 15 it was 17.
So which is it doesn't sound like much, but it's a huge advancement, and this is how we're gonna slowly get there. If we one day get to do nuclear fusion and produce electricity, is it a good thing? Why is it a good thing?
To produce electricity for fission?
Yeah.
Because first, as we said before, there's no debris from radioactive debris.
Debris. Yeah.
A bit from the neutron, I think, but this is negligible.
This is negligible because it doesn't go into the atmosphere, right? It's very local, and at worst it can do some damage to the reactor itself, but it's not going to be going until 10 days later killing somebody, right? So it's not a danger in the way a radioactive material would be.
Yeah. But also fusion is much more safe than the fission, because it can't control itself. It's not like the fission, because we saw it in the Fukushima and Chernobyl crisis. Because in this crisis, the problem is that we did not control the reactors, but here's the reaction control itself.
Right. If it starts going out of control, it'll be so that it'll stop itself.
Yeah.
So it can't get out of control, really, which means that the risk of an accident is much, much lower.
Yeah.
Okay. Do you want to maybe give us a very brief idea what the inertial confinement method for producing fusion is?
Yeah, but we don't use it to produce energy, first of all. There's just one located in France too,
right,
around Bordeaux, I think.
Yeah.
And it's like a beam of laser light. It's a beam of gold that is charged by laser, and it gets instantly in high temperature.
Yeah.
And there's inside the
little cylinder which we're heating up with the lasers.
There's tritium and deuterium, and there are passing in a state of plasma, I think, and there we produce
fusion, but in a very short brief.
Yeah.
So just to complete what you're saying, so the Americans have a big giant laboratory next to San Francisco, and they're the ones who are most advanced in this method. The British also are doing it. I'm sure China is doing it as well. The idea being that you focus a bunch of really, really, really high energy lasers on one little point, and that little point you create a plasma because the temperatures go so high. And then if you put tritium and deuterium in there, in that condition, for a brief moment, you can produce fusion and capture that energy. The difference being that it's not continuous; it's very like short, brief moments. But they're also making advances in that, a lot of it. Okay. Well, I think we've gone through the technical slides. Maybe we can just talk a little bit about the environmental impact and the role that this kind of energy, nuclear energy, can play when we're dealing with when we're dealing with climate change. So let me put the question to you in this way. Would nuclear energy be a useful tool when we want to fight climate change, or is it not that good? Who wants to tackle the question? Clement, I think you seem to be on a roll and everybody's looking at you.
I think it's a great solution because now with the climate crisis, we need a quick solution. And nuclear solution appears to be one.
So let's be specific. We're talking about fission for the moment. Okay.
Just fission. Of course, it. I don't know what to say. It has some dangers, yes, right. But the climate crisis has also a lot of danger, and
right.
I think, as we said before, those dangers are not negligible, but you can deal with them.
Right.
And there's today, nuclear is not that bad comparing to, for example, to the emissions of coal or of
gas, natural gas, oil, any form of combustion.
Because the pollutions in the air is not that great too.
Because if we're, Celeste?
One of the solutions today is to combine several energy sources, not just nuclear, but like also solar energy and everything. Like
the difference being that, so I think we can all agree that nuclear energy is really good in the sense that it's the most powerful source of energy which doesn't produce any greenhouse gases, right? When a nuclear power plant is working, it's not emitting carbon. All the carbon comes from the construction, right? So that's really good. It, like you guys said, it's a good source of base energy, which means that it doesn't depend on environmental conditions, so we can have it at all times. Third of all, we don't need a lot of it, many power plants to produce energy, so the space it takes up is much less than, for example, if we're using solar, if we're using wind energy. There are dangers, like you said. So overall, the dangers are much, 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 much less, or the inconveniences are much less than the actual benefits of it, right?
Yeah, of course. And just to give an example, for example, this 7 grams of uranium is equivalent to 1 ton of coal in energy terms. So nuclear is a real good solution for the future.
The problem would be that it is a very highly technical solution, right, to climate change. So we know how to do it in France because we've been doing it for 50, 60 years. Most Western countries can do it. The problem is that where we need to have good energy solutions is in the developing world, right?
Yeah.
And they don't have that expertise. So how do we fix that problem? I guess it's more of a political problem than anything else in a way, right? And it takes a long time to build a nuclear power plant. And we need solutions which are more quickly as well.
But you said that we need a lot of time to build nuclear power plants. But I know that there are new types of nuclear power plants.
Talk to us about that a little bit, maybe.
So they are called the SMRs.
Right.
Which stands for small modular reactors. So basically, they are like simpler and smaller basic nuclear reactors.
Right.
And they are,
as opposed to like a big giant one which takes 10 years to build. These are much smaller. They have a smaller capacity, but we can build them much more quickly.
And they are built in factories, and they can be
shipped
to different locations. So it's much more simpler, and additionally it costs less money
Right.
to build and to transport.
Right.
And also in the just to add something for the dangers, I think it's also much more safe because most of SMRs are built underground. So in case
and you guys said in your presentation that they're autonomous. So you kind of build them in the factory, you ship it out, you put it to ground, and then it just works on its own for like 60 years.
And in case if there is an accident or something, they are designed to shut down autonomously. So.
And underground means that also there's no radioactivity that would get out easily unless there's like a real, true catastrophe.
Yeah.
Okay. Maybe we can talk a little bit about the political challenges around nuclear energy, because that, to me, seems to be the main problem, right?
Yeah.
The main obstacle. Who wants to talk a little bit about that?
We can talk about it.
Let's go again, Clement.
Of course.
Clement has a lot to say about this topic. This is good.
The political challenges are the most important because, first of all, we need to, as Celeste said, the nuclear energy is the most criticized
most controversial
in the world, and we have to show people that this energy can be good for our future.
So why is it so controversial? Why is nuclear energy? Why do people? I mean, we're five around the table here. We all agree that it's really good, and we don't see where the problem is. Why is not everybody like us?
Because I think there are a lot of not stereotypes, but everyone is afraid of nuclear energy because even I don't know, even in the movies, when we talk about nuclear energy, there are always mutations and everything, even if it's really we saw it's not true, but this is the image of nuclear energy.
Okay, Emma?
Because they're way too focused on all the dangers that are like Fukushima and Chernobyl.
Right.
That doesn't give a good image of the energy.
And I think there's also a lot of lack of knowledge about these accidents, right? So if we look, what were you going to say about that, Celeste?
Yeah, that's what I was going to say about that. And also it affects people directly as other energy might go in the environment and you don't see it affects people directly. So
So I remember reading a statistic when the pollution, for example, around in China in the big cities was really, really bad, 10, 15 years ago, you had more people dying every month from lung diseases linked to pollution than you had in Chernobyl, right? But people keep it in their mind so what was our first image of nuclear energy? Was the nuclear bombs, right? In Japan.
Of course.
And that's that remains in the popular sort of conception of what nuclear is associated together, even though that's two incidents in all of history of humanity.
But nuclear weapons, we have them because when you can't control the reaction, then it's going to get really, really
out of control.
And so that's what happened, I think, in Chernobyl and Fukushima.
The difference being that you're right, but the difference is that to build a nuclear arm, we have to enrich up to what percentage? Do you remember? We have to enrich up to 80%. Whereas, 80% of the material we put in a nuclear bomb is uranium-235. What we use in a nuclear power plant is 5%. So the stuff we have in a nuclear power plant literally cannot act like a bomb because it's too low, the enrichment, right? The danger is if it explodes in a normal way, like a chemical way, and then the radioactive material is spread around. But the problem is also it's a very technical topic, right? So people aren't going to necessarily go and read up on this. And
it's already a new type of energy, new compared to the other energy. So what's new is always, people are afraid about what's new sometimes.
But this is one of the reasons also why, for example, France is the country that emits the least amount of carbon for its energy in all of Europe, is because we're not using gas, we're not using oil, we're not using coal, we're using mostly nuclear. And which is what makes our electricity much more clean, which makes sense then that we do everything with electricity because we're not producing carbon for our electricity. So it makes sense to have trains that are electrical, cars that are electric, heating that's electric. What can we do to educate people? More podcasts like this, right?
That's what I was going to say. Because I listened to a podcast and that is actually exactly what they said. We have to like educate more people. I think the name of the podcast was Parole d'expert.
Okay.
and our podcast, of course, but I think
the name of the podcast was
this
Physics
one
Bites.
is much more like national. And
Right, it's a bigger audience.
Yes.
For now.
But they also talked about missions of so the International Atomic Energy Agency comment on dit mettre en place?
To put into place.
Put into place protocols, and you can
Apply them?
apply to them, and you can. I think it's like
Volunteer based?
Volunteer based.
Yeah. Okay.
So, and it's for not every age, but I think you have to.
There are things in place where you can
Yes.
sort of educate yourself. Are you going to go and, like, become
Why
militant activists for nuclear energy with
Why
your
not?
friends and family? Yeah, Celeste?
I'm doing maybe it's not. I want to do something with an engineer in nuclear.
Mm-hmm.
He's in Montparnasse,
Okay.
and maybe I'm gonna work with him.
Oh, that's interesting. So maybe then next year when you're in our final year, you'll tell me in our podcast about stuff that you did with him. Yeah. Colombe?
I think, of course, it doesn't really apply to us, but of course, research is important.
Right,
That's,
right.
That's why.
I think one of the things we've learned is that, so France used to be the leading country in terms of knowledge about nuclear energy, but for a lot of political reasons and other reasons, we've lost a lot of that knowledge. And, we have many other countries like India, like China, which are catching up and getting past us, right? So we didn't, for example, talk about a lot of modern ideas for nuclear power plants, like thorium-based power plants, which don't use uranium. Now we have countries elsewhere that are doing this, and we're kind of losing that knowledge in France. Emma, you were going to say something.
I was just going to say that, like they said, educating ourselves is really important, because I think before doing this project, we're all like, "Oh, nuclear is bad," and
right, because we all sort of have that collective idea of nuclear explosion,
I
bad
guess.
mutations.
But once we talked with the expert, like he talks about how the dangers are not that high risk.
Yeah.
And we have solutions like radiation, iodine radiation. If we take iodine tablets,
Right.
it can prevent us from getting thyroid cancer.
But even if we take in, for example, a lot of radioactive iodine, which is one of the byproducts of nuclear fission from uranium, it won't stay in our system long enough for it to cause a problem like thyroid cancers and stuff like this, right? We have a lot of knowledge, we have a lot of solutions. The problem becomes, I guess, education, like communication, how do you present the thing? It doesn't help that in most movies, nuclear is not really shown in a proper light. Okay, I think we've gone through most of the topic and most of the stuff you talked about. Maybe we'll finish up on, you kind of already started talking about it. What did you guys find most interesting during your research about this topic? Maybe something personal, or maybe it was because of the contact with the person. Why don't we go through each of you guys and what you found most striking in your research?
So personally,
Celeste.
I already said it, but I didn't know that it was good for the health, and I was really surprised by this. I think this is the most
okay. I suppose it depends on the dosage that you get, but we do have what we call nuclear medicine, right? In nuclear medicine, we treat many cancers with radiation and radioactivity in a very specific way, right? So nothing is ever just good or just bad, right? It all depends on how we do it. Colombe, in your experience, what did you find interesting?
Well, I worked basically on the projects and the innovations for the future, and it's really interesting because there are so many projects and things that are taking place today, and I think nuclear energy, if it is used well, it can solve like really a lot of actual problems, and it's this like really
the potential for the good it can do is very high.
Yeah.
Okay, that's reassuring. Clement?
My point is quite the same, because I was a bit against nuclear firstly, but like to learn more about it helps you like be for nuclear.
You've been converted.
Yeah, if you want, but also about fusion, I didn't know that we could produce energy from fusion, and I think it is a key
solution for the future,
of course.
Yeah, the problem with fusion is that for the last 70 years we've been saying we're going to have fusion in the next 30 years, right? It is a very technical challenge, but we're getting there slowly, and I think maybe within a couple of decades, 3 decades, maybe we'll be able to actually use it as a main source of energy, but still a bit far off, right? Emma, what about in your experience?
I would say the same as Clement and Colombe. But what struck me the most was how all of our thoughts on it wasn't quite similar as the reality, and how it's innovating each day and each year. So that's really great.
I think it's interesting what you bring up, because I think so. You're saying that specifically about nuclear energy, you thought you knew a lot of things, and in reality, you knew not much, and your opinion was based. I'm sure that's true for many things, right? In general, we have far too many opinions that we're convinced of, which is based on very little in general, whether it's scientific, whether it's social or economic or political. Okay. I think we have gone through most of the stuff, so thank you very much. It was a very interesting presentation. I think I'm glad to hear at the end that you guys have found that it was able to change your opinion on a lot of things and have a better sort of understanding of the science behind it, and so take away the danger and the fear that goes with it. So thank you very much.
Thank you.
So that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.